Good day, everyone, and welcome back to my calculus class. This time around, we want to be looking at the concept of antiderivatives, which we can also refer to as the reverse of differentiation. So, from the word anti, so that is the reverse, that is undoing derivatives. Okay, so let us look at some basic definition. A function, say we call it capital F, is an antiderivative of the function, let's call it small f, if by the time we take the derivative of that big F, if it is equal to the small f for all x in the domain of F, then we say that that capital F is the antiderivative. This is what we are saying. Let's say we have some function, say capital F of x, then I call it, say, cosine of x. Then if I say f of x is sine of x, let us check if um, this capital F of x is the antiderivative of this small one. Okay, now the question we need to ask is that if we take the derivative of sine of x, what are we going to add? So if we take the derivative of sine of x, we do know that it is cosine of x, which is this. So in that case, we will claim that cosine of x is the antiderivative of sine of x. So that is what the definition is saying. And we also notice that from these other examples, I can ask you that what is that function that if I take its derivative, I am going to get 3x squared? Well, maybe you're already thinking that if we take the derivative of something like this, we will get 3x squared, right? If we take the derivative of something like this, x cubed, so if we take the derivative of x cubed, then what are we going to get? Um, we'll get 3x squared, right? Now, in this case, we want to find the antiderivatives, meaning that we will think of a function such that when we take its derivative, our result is going to be 3x squared. And in this case, we find 1. However, we will quickly notice that, is that the only function that can give us that uh, result? Maybe not. For example, if I add 5 to this, if I take derivative of this function, if I take derivative of this function, then let's say I want to take derivative of this, so that is 3x squared plus 0. So it is still 3x squared. Even if this is 6, even if this is 60 or 600 or 1000, it doesn't matter since the derivative of a constant is 0. So we are still going to have 3x squared every time. The same thing with, if I ask you that what is that function that when we take its derivative, then it is cosine of x, you will tell me that, well, we just did it the other time. It is sine of x. However, even if we add any constant to it, say 10 in this case, if we take the derivative of this function, if we take the derivative, you would notice that we still have cosine of x. So in general, we would say we must add a constant c to the function that we derive. So we must always add a function to any antiderivative. I hope that makes sense to you. Okay, now with that, it turns out that in this case, we will have to say, well, f of x, that is the antiderivative, is x cubed plus some constant. The same thing in this case, we will have to say the antiderivative for this function is sine of x plus some constant. And again, if I ask you, what is that function such that when we take its derivative, it is e to the x? Well, that is easy. We have learned that it is e to the x, and we need to add some constant. Also, if I ask you, what is that function such that when we take its derivative, it will give us natural log of x. When we take its derivative, it will give us uh, natural log of x. Well, you remember that if we have, um, uh, let's see, I should put here 1 over x. Okay, so if I ask you that, what is that function such that when I take its derivative, it is going to give me 1 over x, then you should be able to say, well, it is this function, natural log of x. We have learned this in the past. If we take the derivative of this function, then it is 1 over x. However, we need to be careful with natural log because the domain of natural log, our input has to be positive. So in that case, I will introduce absolute value there. So in general, the antiderivative of 1 over x will be something like this, natural log of x, but in absolute value, then plus c. So that is just a quick example. Now let us study some notation. Given a function, say small f, given a function, the indefinite integral, this notation, the indefinite integral of f, denoted by, look at it, elongated s. Please do not write this. They are not the same thing. That is letter s. We need this, elongated s. Okay, so this elongated s, so we write this dx. We call it the indefinite integral of f is the most general antiderivative of f. So if capital F is an antiderivative of that function small f, then we say this, the antiderivative of this function is going to be f of x plus c. So this is the notation that tells us that we are looking for antiderivative of a function. And the f of x is called the integrand. That is, this f of x is the integrand. And what tells us about the variable of integration is this dx. So, and the variable x is the variable of integration. And yes, this dx is very important. We need to put it there because it shows what are we integrating in respect to, or with respect to. For now, I will just leave it as such. In your next class, you are going to learn more about this dx. Okay, now we have learned some definitions and we have learned some notations. Let us learn some rule. Let us learn some rule. So we say there is a power rule for integrals. Now, we want to be careful by saying our n in this case is not equal to -1. And if that is the case, we say if we're taking the integral of some power function, so let's say x raised to the power n dx. So we want to be sure that our n is not -1 in this case, because if it's -1, we will see what will happen shortly. So in that case, it happens that we are going to add 1 to the power And whatever the result is, by adding 1 to the power, we divide it, the whole function by n plus 1. Let us quickly go back to this function here. This is an example. This function here. So I asked you the other time to give me a function. We did not know how to get there, but because it was easy to find, so I could just say, give me a function such that when I take the derivative, when I take its derivative, it is going to give me 3x squared. So you guys were able to tell me, but what you did was this. You added 1 to that power, and whatever you add as the result in the power, then you divided the result, everything, by that new power. So that is 3x raised to power 3 divided by 3. So this can cancel this. Then you have x raised to power 3. So that was what you were doing internally. So we just made it a rule. We call it power rule, which says just add 1 to the power, then divide everything by that new power. And like we said, you need to add C, constant of integration. Now, why do we want it to be different from -1? Look at this. Suppose we have -1. If we are adding, let's say we are adding 1 to that, so which means we need to divide by that new result. So we will be having x raised to power 0 divided by 0, which does not make sense. We cannot divide by 0. So that is why we do not want our n to be -1. So that is why when we have this, we say the antiderivative is something like this. So you see, it is unique. Okay, I hope that makes sense. So there is also a constant rule for integral. So which is simply when we have constant, if we are integrating constant, it just simply becomes dx. And also, if I ask you that what is the derivative of, let me put it this way. If I ask you that, give me a function such that when I take its derivative, my answer is 2. Well, you guys will tell me that maybe something like 2x. If I take the derivative, it is 2. What if I have 3? What is that function such that when I take its derivative, it is just 3? Well, you will tell me that it has to be 3x, because if I take the derivative of 3x, it has to be 3. So remember, we had to add constant of integration. So that is exactly what is happening here. So we say the antiderivative of a constant function is k multiplied by that variable, kx. So kx plus c. Let us look at some common differentiation formulas and their corresponding indefinite integrals. So it's just, remember, reverse, just going backward from what we have learned. Okay. So remember that if we take the derivative of a constant, then it is going to give us 0, right? So now, if we then say what is the antiderivative of a constant? What is the antiderivative of a constant? Let's say k. We just settled that earlier on anyway, so I just show you that. Now, look at here. If we take the derivative of x to the n, it is nx n minus 1, the power rule for differentiation, you remember? So the same thing, I can say if I want to take the integral, what of this? If I want to take the integral of this function, then it has to be, okay, let me just focus here, then we can move sideways. Okay, what we are saying is if we want to go backwards, the reverse, ddx, ddx of x to the n is, remember how to do this, power rule, we do this. Now, if I want to go back, then I will introduce this, nx, n minus 1 dx. So if I do that, that means I need to add 1 to this power, then divide everything by the new result in the power. So that is nx raised to power n divided by n. So n cancels n, I have x to the n. Okay, the same thing with here. So we have it here. So I've explained this the other time and this and so on. Um, so and so on here. So I'm saying if I take the integral of cosine of x, it is sine of x. Now, if I take the integral of negative sine of x, that is what gives me cosine of x, and so on and so forth. So in integral notation, look at it, for example, if I take, that means if I take the integral of 1 over x, it is natural log of x with absolute value. If I integrate e to the x, I get e to the x. If I integrate cosine of x, then I have sine of x. All what you need to do is ask yourself, what is that function, such that when I take its derivative, it is going to be this cosine of x. So, and that is sine of x. Again, here, look at it. What is that function such that if I take its derivative, it is sine of x? That is what we are asking here. So it turns out to be negative cosine of x. If you want to check negative cosine of x, take the derivative of this. You will see that that is minus cosine of x itself. The derivative is minus, sine x. So which give us sine of x. So that is the antiderivative, and so on and so forth. So which means the integral of sine squared of x is tangent of x. Again, how do we know? If you take derivative of tangent of x, it will surely give you sine squared of x, and so on and so forth. Okay. Okay, let me also explain some other things about inverse trigonometric function. You remember that when we learn the derivative of inverse trigonometric function, we say the derivative of this, do you remember? The derivative of that function is 1 over square root of 1 minus x squared. So, which means if I integrate this, if I'm asking you what is the integral of this, you have to tell me that it is sine inverse of x. And also, what about this? 1 over 1 plus x squared dx. You remember, like I said, anytime you use this sign integral, you must put dx to show that variable you are integrating with respect to. Now, in this case, I'm simply asking you to give me that function such that when I take its derivative, my result is 1 over 1 plus x squared. And as you remember, that should be tangent inverse of x. And as usual, we need to add plus c. So the same thing with what we have here. So these are all just the formulas you can make use of. Now, just repeating here, notice how we add C. So, and that is because it is referred to as family of antiderivatives of f. Because the other time when we add, say, 3x squared dx, the antiderivative of this, we said we have x cubed. But it could be plus 1, it could be plus 2, it could be plus 3. So there are infinitely many of them. So to avoid that situation, we just say plus C, and we call it a family of function. We say this is a family of antiderivative, antiderivatives. And also we call it general solution to this integral, indefinite integral. So we call it general solution because, well, it is general because C could be anything. C could be anything. How do we know if an antiderivative is truly the antiderivative of a particular function? Well, no problem. Just take its derivative. It has to give you the integrand. It's as simple as ABC. So, example, each of the following statements is of the form, that is, we have the uh, function inside an integral, so which means we are looking for antiderivative. So, it is of this form, meaning that you have been given the supposed antiderivative, and I want you to verify if each statement is true. And that is just simply by saying check if when you take the derivative of the antiderivative, if it is going to give us this. Let us try that. So let us say our f of x is x squared over 2 plus e to the x plus c. So let us take derivative of this function. So this is 2x over 2 plus derivative of e to the x is e to the x. Derivative of a constant is 0, so gone. So this is x plus e to the x, which is essentially what we have here. So this is true. This is true. And that tells you that the antiderivative of this is x squared over 2 plus e to the x plus c. Let us check the next one. So the antiderivative in this case is x e to the x minus e to the x plus c. Let us simply take derivative of our function. I can apply product rule here, right? Yeah. So derivative of x is 1. So I will just say e to the x plus. Now I will keep x. Derivative of e to the x is e to the x. So minus derivative of e to the x is e to the x. Derivative of c is 0. So this will take care of this, and I will have x e to the x, right? So, which is the same thing we have over there. So truly, this is the antiderivative of that function, x e to the x. So I will just leave you to verify this, if it is the antiderivative. Okay. Now, let us learn some properties of indefinite integrals. Very simple, just like we have learned with continuity, we have learned with differentiation themselves, and so on. So even with limits. So here as well, same thing. If we are having two functions and we want to add subtract under integral, well, no problem. You can separate it by this g of x dx. So we can say that is integral of f of x dx plus integral of g of x dx. And remember, all of this will give us f of x plus c. All of this will give us g of x plus c. Well, since any constant plus any constant will give us another constant, so that means our answer is f of x plus g of x plus constants. It's still constant. So that is the formula. In simple terms, it means take the derivative of, find the antiderivative of each function. Subtract or, so what if we have a multiplier with a function? No problem. You can just kick the multiplier out since there is no variable with it. So it is just a multiplier. So you can just kick it out. So you have k f of x plus c, and so on and so forth. Let us take a look at example. This is 5x cubed, 7x squared, 3x, 4. Well, the antiderivative here, got it as a equals to, the rule we just learned say we can take the antiderivative of each of them, dx minus 7x squared dx plus integral 3x dx plus integral 4 dx. So this is using power rule. We can use power rule since it's a power function in each case. So we can just say this is to the fourth over 4 plus c. But instead of writing plus c, this place, having find it plus c, I will just reserve it to the very end. So here is 7x raised to power 3 over 3 plus c, but I will reserve it. That's 3x squared over 2 plus, here will be 4x, then plus c. So it is important I write it there. And guys, this is our results. If you can simplify it, you can simplify, but in this case, that seems to be the last step we should be having. Okay, we look at that. Let us look at another example. What we have here is looking complex, but we can start by simplifying. So what if we say x squared over x plus 4 times cube roots of x over x, so dx. We can do that, and well, we can say this is x plus, here, this is 4x raised to power 1 over 3. Remember, that is cube root 1 over 3. So divided by x dx. So x 1 over 3 divided by x, that is x 1 over 3 minus 1, right? So that is x raised to power negative 2 over 3. So we have integral x plus x negative 2 over 3 dx. And by the property we just learned, we can separate them. So that is x dx plus integral x negative 2 over 3 dx. So if we find the antiderivative now, using power rule for this, we can do that, yes. That is x raised to power 2. That is, there is 1 here. There is 1 here. So if we add 1 to that, we have 2 over 2 plus here as well. That is x raised to power. If I add 1 to this, so that will be negative 2 over 3 plus 3 over 3. So that is 1 over 3. Now I need to add plus c. You must add plus c. So guys, that is what we have in that case. Remember, we will not be able to use the power rule if what we have here was 1. That is negative 1. That is the only situation when we cannot use power rule for power function. Okay. Now, there is one here that I want you to look at. Look at this. Oh, sorry, I made mistake somewhere here. There is a 4 that I left out there. That's over the excitement, solving that. So there is a 4 here, so we need to keep carrying it. It is just a multiplier, so just keep carrying it to the very end. So that. Okay, so this is try it for you, but let me try to, since I might not be able to respond to your answer. So let me just say we have 4 over 1 plus x squared dx. In this case, we will not be able to simplify it as we did here, right? We will not be able to do that. But you would notice that I can write this as 4 into 1 over 1 plus x squared dx. And remember, this is a standard derivative for a particular function. And what is that function? It is tangent inverse. So I have 4 tan inverse of x, then plus c. Answer. It is as simple as that. These are not going to solve it for you, but try to solve it by thinking. Can you simplify this integral? Try to think about you simplifying it and see if it is going to um, reduce to something you can find its antiderivative straight up. This is just an example of what we just had earlier there. So try all those problems. Now, we want to look at some special application of integration. Here, we turn to one common use of antiderivatives that arises often in many applications, and that is solving differential equations. So we'll just scratch this at the surface, then we'll leave it for now. But let us learn the definition. A differential equation is an equation that relates an unknown, function and one or more of its derivative. It is simple. It's saying, suppose we don't know some function. We don't know it. So let's say um, f of x. But I have f of x, now you combine it with its derivative, maybe one or two of its derivative, then we say and you use it to form equation, then we say it has become a differential equation. So it's an equation that relates an unknown function and one or more of its derivative. For example, suppose we are giving this simple example of a differential equation, dy dx equals to f of x. That is our function, f of x. Now we relate it to something like this. Its derivative. So it is also possible that we relate it to maybe its higher order derivative. We can do that. So that is what we are saying. We say it is a differential equation. All right. So to find that function y, we need to integrate both sides. We need to integrate both sides. Remember, if I have dy dx, if I want to go back, that means I have y, right? And to go back, I need to introduce the integral sign. That is to find the antiderivative. So, which is that? And now if I do that here, so I do this, and that means I need to do it on both sides. So if I do that, then this will automatically go back to y. That is the antiderivative of dy is y, right? So in this case, let me show you what is going on here, f of x. So then I can introduce dx to both sides, dx. So this can take care of this, and I have integral dy equals to integral f of x dx. And if I go back here, I will have y, right? So that is integral f of x dx. So then I can have that situation. So look at it, that is that function in this case, y equals to integral of f of x dx. But indefinite integrals always include a constant of integration. And what does that mean? Like I said the other time, it is called general solution. That is, there are infinitely many solutions because of that constant. Now, it is possible that we are just interested in a particular situation. So we call that solution we have in that case as particular solution. What do I mean? Maybe you have a function that represents the population of a particular city at the time. But like all the times, but you are interested in just, let's say, at time t equals to 0. So you want to look at it at that particular time. What is the population, right? So that is what we mean by particular solution. And that occurs when we apply the initial condition. The initial condition gives us a point on the curve of the function. Suppose we have this curve representing that function, and we say at time t equals to 5, our population is maybe something, right? Maybe at time t equals to 5, our population is 1,000. So it is always a point on that curve. I hope that makes sense. The initial condition we'll give is always a point on that curve that can tell us, you know, that can help us with the solution of that function. Okay, let us look at example. Example, let dy dx equals to 2x. Y of 1 equals to 5. This is the initial condition. Now, the question is asking us to find the general and the particular solution. You can see this is a differential equation. We have some function together with its derivative. So when we have initial condition with it, then we say we have initial value problems. So in this case, it is an initial value problem, which is also referred to IVP. IVP, people call it. It is very popular. IVP, initial value problem. Now, let us try to solve these problems. So in this case, we do know that to find that function y, we just need to do this. Just need to do this, dy dx equals to integral 2x. So we're integrating. Since you have this sign, you have to introduce the dx. Okay, and we have that this will take care of this. So we have integral dy equals to integral 2x dx. So here we will have y equals to, what is the antiderivative of 2x? Remember, all you need to do is add 1 to the power, then divide it with the new one, since it's a power function there. So that is 2x raised to power 2 over 2. Remember, plus c. You have to add plus c. And notice that once I find the antiderivative, I do not bring this sign here again because I have used it. It is gone. So I don't rewrite it. It's like if I'm taking the square root of 9, I will just go ahead and say my answer is 3. If I still keep that square root, then I'm wrong because they are not the same thing. Okay, so please take note of how to use the notation rightly. Okay, so these two, we take care of these two, and we say y, that is our function, our non-functional y is, now we know it's x squared plus c. However, in this case, what we have here is the general because it is having c, general solution. Now, to find a particular solution, we will need to use our initial value. So, and what this means is that when x is 1, y is 5. That's what it means. 1,5, that's what it means. So when x equals to 1, y equals to 5. And that implies that we can replace y by 5 and x by 1. So 1 squared plus c. So which means c in this case is 4. 5 minus 1, that is 4. And we can claim that we have our particular solution, which gives us, therefore, we have y equals to x squared plus, this is the simplified one. So here, so y equals to x squared plus c. Our c is 4. So this is a particular. So in this case, we know exactly that function. So particular solution. So guys, that is that. As simple as that. What about this? Well, no problem. All what we need to do is say dy equals to, in fact, I can write it this way now, since you guys know what I'm trying to do, sine x dx. And now that gives us y equals to, the antiderivative of sine of x is negative cosine of x. Don't forget. And I must add plus c. So this is my general solution. My general solution. Now to find the particular solution, we can see that when x is 0, y is 5. So we just use it. 5 equals to negative cosine of 0 plus c. So that is 5 equals to cosine of 0. Cosine of 0, you know what it is, right? Cosine of 0. So that is 1. So negative 1 plus c, right? I will still remember how to find all those values from your unit circle in your head at this point. You should know, right here. See, this is when your angle is 0. So cosine of 0 there is 1. Okay, now c equals to 6, and we can say our particular solution, y equals to negative cosine. You're just looking for the value of c, that's all. So plus 6. That is the particular, solution. Particular solution. So there is one here for you to play around with. Let us also solve an application of initial value problems, which is very applicable to our real world. We drive like we learned in the past, the calculus of driving. We have dealt with it several times in this class. You say a car is traveling at the rate of 88 feet per second, which is 60 miles per hour. 88 feet per second. That is the rate at which the car is traveling, the velocity, right? Okay. When the brakes are applied, that is, the speed, the car begins decelerating. So the car has been traveling, then all of a sudden it applies brake. So I want to say from the point where it applies brake, let me say here, I'm accounting for when it applies brake here. Okay, the car begins decelerating. So that journey of deceleration, that is what I want to account for. Okay, from that point where it starts to decelerate, let's see what happens. But remember, the car at this time, 0, I will call it 0 because that is the time I start measuring when I apply brake. Okay, so that is when my time starts counting, right? Now, at that point, I can say the velocity is traveling is 88 feet per second at that time. So it starts to decelerate. So which means I can say the deceleration here is negative 15 feet per square second. And remember that continues throughout the journey, right? That continues throughout the entire journey because it's a constant deceleration. It is a constant deceleration. Okay. Now, look at it. If you are traveling at 88 feet per second and you are decelerating, which means by the time you are getting here at the final time, your velocity will be 0 because you are applying brake. So that means you are going down, like you are reducing that speed until it comes to a stop. So the question is, how many seconds elapse before the car stops? How many seconds elapse before the car stops? Well, um, let us see if we can form some initial value problems here. Something I notice is even though I put a of 0 here, I can conveniently just call it a of t because it is the same thing at all time, right? At all time. But I cannot do that with v because v is changing based on the acceleration I'm applying. So that velocity is changing until it becomes 0. But I can claim my a of t is negative 15. And I say negative because it is going down. Now, let us see what we can formulate here. First and foremost, I notice that acceleration is the derivative of velocity. And this acceleration is negative 15. Look at something here. I can form an initial value problem because I know that at 0, the velocity is 88. So if I want to write out my initial value problem out very well, then I have v prime of t equals to 15, negative 15. Actually, when t is 0, v is 88. And guys, I have initial value problem. Remember that v prime of t is dv dt. So which means if I take the antiderivative of this, I need to add dt. So I do the same thing here. That is negative 15 dt, right? So in this case, if I find the antiderivative of v prime of t, remember, the question we're asking there is that give me that function such that when I take its derivative, it is v prime of t. So that function is just v of t, right? So v of t equals to, if I integrate negative 15, I will have negative 15t, right? If you are still not sure at this point, if you take the derivative of negative 15t, what will you get? Negative 15. So try to move back and forth in that sense. But I must add c. So that is a general function for velocity. Let us find a particular function now. That is when time is 0, v is 88. Since we know that, then we can say when t is 0, v is 88. So we can plug it in here that 88 equals to negative 15 times 0 plus c. So our c is 88. And in general, v of t, therefore, v of t equals to negative 15t plus our c is 88. So 88. We have that. Are we done? No, we're just being able to find a function in terms of velocity. The question is, how many seconds elapse before the car stops? That is there's a clue there before the car stops. We know that when the car stops, that function that we have now, v of t that we have, will be 0 when the car stops. So we know that when t, well, we don't know that t, but we can say um, at the end of the journey, at the end of the journey, v is 0. So we can say 0 equals to negative 15t plus 88. So we can find our t, right, at the end of the journey. So the time t will be, so we can move this, negative 15 becomes positive, equals to 88. And we can divide this, so that is t equals to 88 divided by 15, whatever that is. So the unit is seconds. That is that. And now, The second question is, how far does the car travel during during that time? The question of how far, that has to do with um distance, right? Distance. So that is, we want to find the distance covered from that point when the brake is applied to the end. So let's call it S of t. Now, um, we can also do something here. At the very beginning, we know that distance is zero. At the beginning, the distance covered when you start to apply brake, boom. At that point, the distance is zero. So at the end here, that is what we are looking for. S of t, what is it? So you can see I've been able to find initial value here. Let us see if we can create an initial value problem for distance. And that comes again that if I differentiate distance, I will get velocity. The rate of change of distance is velocity. So I remember we already know velocity. We know v of t, which is the same thing as if I take the derivative of distance. Now, what is that velocity? We just find it here. We have a function for that. We have a function for that. That is negative 15t plus 88. So which means I can put it here, negative 15t plus 88. Now, let us see if we can form initial value problem. S prime of t, that is ds dt, equals to negative 15t plus 88. And we know that at time t equals to 0, the distance covered is 0. Boom, we have initial value problem. We have initial value problem. Now that we have this, well, to find that function, I just need to take the antiderivative of this, t equals to integral negative 15t plus 88 dt. You must put that there. So if I integrate s prime of t, I will get s of t, right? Okay, so equals to, I will keep my c here since I'm going to add c to the other side. So that's why I do not bother. So in this case, this is negative 15t squared over 2 plus 88t, then plus c. Now to find our c, we need to find that c. That is where the initial condition comes in. So when t is 0, when t is 0, s is 0. So we just plug it in there. That is 0 equals to, if I plug in 0 for t here, so everything becomes negative 15 0 squared over 2 plus 88 times 0 plus c. And our c is 0. So which means that that function s of t will be negative 15 t squared over 2 plus 88t. So the question of how far, we know the time taken. The time taken is 88 over 15 seconds. So s of 88 over 15 seconds is, actually it's just plugging your time. 88 over 15 all squared over 2 plus 88 over 88 times 88 over 15. So in this case, I will leave it this way since you guys are not using calculator. So I'll leave it this way. But if you have something easy to work with, what I mean by that is, suppose instead of 88, suppose we have, let's say 90 over 15. You can still be able to simplify that easily because that would be 6. So you can square that and so on and so forth. But in this case, I will take that answer in that situation. But something is important, the unit. Since it is distance, so the unit is feet. So I don't want this video to be too long, so I'm going to be ending my video right now. So this is But these are some try it that you should try to work on. And with this, I will say thank you for watching this video, and this is the end of Calculus 1. So in your Calculus 2, you will learn more about integral calculus. So bye for now, guys.